So, applications of exponential equations or exponential models. You can read for yourself there. Many situations in which varying a quantity can be modeled by an exponential function. You've seen some of these before. We've talked about some of these. We are going to go through a few of them. We will do an example or two from the book. Then we'll go through one of Mr. Bransgrove's PowerPoints. As you would know, that's often a handy thing to do to get a feel for the sorts of things he may put on an exam. So that'll be worth doing. So let's start with example 34. After 1,000 years, a sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life of radium-226. Radioactive decay, decaying by a percentage, a constant percentage each time. So it can be modelled, as we saw last lesson, using the formula A equals A naught e to the KT. What are we going to do first? Who's got any suggestions for me? Oh, Kate, it looked like you wanted to say something. No. So whether you have A or N, doesn't really matter. I'd probably,
I just moved it to the side.
Oh, you just moved it to the side. All right. Oh, sorry. It's disappeared. All right, well, let's find the amount that we have left. You could have so you're going to have to define a variable. Let A equal the amount of radium 226. Is that fair enough? What's our equation going to look like? The amount of radium is going to be A naught. Now, it's nice if you can say A naught equals the original amount. E to the KT. Now, sometimes you would have seen yesterday they had a negative K in there, or maybe I'm thinking of my specialist maths in grade 12. But a negative K is kind of annoying because K can just be a negative number. You don't have to have negative K there. You can just work with the fact that K is going to be a negative number. After 1,000 years, the sample has decayed to 64.7%. How am I going to use that information in this equation? Well, 64.7% is going to be the amount that I have left. Is everyone happy that that's 0.647 multiplied by whatever I started with? No? Yes? Maybe? 64.7%. Percent means out of 100 divided by 100. 0.467 of its original mass. Well, I've said A naught is the original amount or original mass. So 64.7% of the original mass, 0.647 A naught. And that's going to equal A naught E, and T was going to be 1,000 K. We all right to that? 1,000 years, so I let T equal 1,000. Now I'm just going to solve this. Well, first thing I'm going to do is divide by A naught. A naught's not equal to 0. I had some amount to begin with, so that's okay. 0.647 equals e to the 1,000k. I'm going to reverse my log definition, aren't I? Logan and Knack's form. This is a number equals a to the x, so I rearrange it and I go, in this case, the base was e, so I'm going to write natural log. If you wanted to write log base e, that would be okay as well. But I'm going to go with natural log of 0.647 is equal to 1,000k. Divide by 1,000 and I've got my k. 647. Now, have I answered the question yet? No, what's it ask us to find? The half-life. So the half-life, not everyone does chemistry, half-life is how long it will take for half of the original amount to be there. So I've got my full equation now. I can write my full equation. A equals A naught e to the ln 0.647 over 1,000 t. You see, I don't need to figure out what k is, try and write it as an approximate decimal or anything. Just keep it as a full value. Now I'm going to say let a equal half a naught and solve for t. So half of my original mass equals the original mass multiplied by e to the ln of 0.647 over 1,000. And we're just solving this now for t. Good news. A naught's not equal 0. I can cancel that again, can't I? How am I going to rearrange this equation? What am I going to write? The log of 1/2 base e. What's the other way we write that? Natural log, so ln of 1/2 is going to equal, what was the power on the other side? ln 0.647 over 1,000 multiplied by t. So t on its own is going to be 1,000 log of 1/2 divided by the log of 0.647 multiplied by the reciprocal. I'm changing to approximately equal to because someone's going to help me out, push buttons on their calculator and tell me how long that was. Maybe you'll all do it and you'll make sure you can use your calculators and do that correctly. You may need to use the brackets on your calculator. Oh, I know, there are brackets. ln, natural log, so log base e. It's the ln button. Oh, we're taking so long, I'm going to pause. So we do that, and we've got 1591.95 years. Is that a reasonable answer? That could be a question in your exam. Evaluate the reasonableness of your answer. How do I know that's a reasonable answer? I don't really know about the half-life of radium other than what they've told me in the question. So I go back and I look at my question. After 1,000 years, I was left with 64.7%. I'm working out the half-life, which would only be 50% remaining. So that's a fair bit more to decay still, isn't it? Is it reasonable, therefore, to think that it's quite a bit after 1,000 years? I know it's going to be less than 2,000 years. How do I know it's going to be less than 2,000 years? Well, that's what you're thinking. How would I know it's less than 2,000 years for the half-life? What percentage am I left with after 1,000 years? 64.7. After 2,000 years, what percentage would I be left with? 0.647 squared. Wouldn't the next 1,000 years, 64.7 of whatever I had remain? So if I do that on my calculator, I know that that would be the amount remaining after 2,000 years. I've got a good idea of where my answer should be. I don't know what 0.647 squared is, but I know what 0.65 squared is. What's 0.65 when you square it? I taught you guys how to do this in grade 9 and in grade 10. Square a number ending in 5. 65, take the 6, multiply it by 7, 42. Stick a 25 on the end. Someone remembers. That you here? Good. Jürgen, did you have to tell him? Probably. Oh, the calculator. Oh. Well, we know that would have been 40%, so I've got to be less than 2,000. Yeah, our answer is reasonable. We're all happy with that. No pressure, no dramas. All good. Let's find you another question to have a go at. Thinking about opening. I think it'll build suspense in the video if I keep it running.
Yeah, definitely.
Oh, wow, now I wonder what it's recording. Hopefully it's still recording the full screen. Oh, we've got a display settings. We just want it to be. Oh, wow, the exponential growth of computing. That's an interesting picture. E is not a number. We know that. We've been over that. We don't need to worry about that. Let's get to a question. Okay, here's one we can have a go at. The radioactive element carbon-14 has a half-life of 5750 years. A piece of charcoal that had lost 7.3% of its original amount of carbon-14 was discovered from an ancient campsite. How could the age of charcoal be determined? Or better still, why don't you just have a go at determining the age of the charcoal? That's an unusually worded question. Have a go. I will pause to give you a chance to think about it. So we start with the rule that we need to know. Well, it almost started with the rule. Well, we start with A equals A naught e to the kt, and they've now substituted in the first value, haven't they? Half-life means I've got half of the original amount. That's why it's 0.5 A naught over 2, half A naught, don't care how you write it. That happens when it's 5,750 years. So we've replaced T with 5750. The objective, of course, is to find the K for this particular rate of decay. We go ahead, we use our log laws, and we've got a nice exact value for K. As Ms. Kinnear was showing in the DO9 room, you can store that on your calculator and save it, or I'm just going to substitute it in brackets like that when I'm doing my working. Either one's fine. Efficient use of your calculator, though, dictates that you could do that. We don't want to see you using that value unless they've asked specifically to write down that value. In your exams, giving an exact value, unless they specify they want it to a certain degree of accuracy, give the exact value. We've got the exact value, now we've got to do the next bit. If 7.3% of something has decayed, how much remains? 100% minus 7.3%, 92.7%, but we've got to express that as a number, so 0.927. We go ahead and we do that. 0.927 A naught equals A naught e to the kt. We now know, we rearrange, the amount of time that would have taken, how old this particular piece of charcoal is, can be determined. We substitute in our value from K before, and you're getting approximately 628 years old. Pedro claims 629. What did you get on your calculators? 628.8. Fair enough. I think 0.8 of a year, 0.4 of a year, we'll cope with it either way. But yes, round correctly, please. That would be good. Now, here's interesting. What was the number in our last question? 5750. What does this one say the half-life of carbon is? 5715. Crazy, isn't it? Obviously, they're using calculations to calculate these, but they weren't alive 5,715 or 50 years ago. So you've got to be careful. Maybe someone misheard 50 and wrote 15. Maybe someone misheard 15 and wrote 50. Maybe they just got different answers in the particular experiment they're looking at. Either one will be okay. Careful not to round too early. So, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. Another good example. Have a go at that one. All right, running through it. Let's make sure we've got this right. So we start off with our, it's got to let me do it first. A equals A naught e to the kt. Substitute in the value and find the K value for carbon-14 using the new number of 5715 instead of 5750 from the previous question. Oh, I really don't like the way they've typeset that. ln of a half, never use slashes, horizontal vinculums. Only, please, vincular, maybe. Solve for K, they've got K equals that very tiny decimal. You wouldn't bother writing that, you'd have ln of a half over 5715. We go ahead and substitute that into the model. What am I going to use for my A? If I have 73% remaining, or 76%, I just use 0.76 A naught. In the previous question, they told me how much had gone. So I had to go 1 minus that to find out how much I had left. This time they told me how much I had left, so I don't even need to do any maths there. Divide by A naught, simplify using your log laws. How did we go? Did we get approximately 226 8 years. All right, there we go. So let's correct the... Maybe it's because they've rounded off the K value. Maybe it's because they're supposed to be using 5750 instead of 5715 that we're getting a different answer there. You can explore that for yourselves. It doesn't really matter. The point is the working and how you go about it you can do. Are we happy enough with how we can do those? All right, let's see if we can find another question. All right, culture of bacteria grows and it obeys the laws of uninhibited growth. So it's just going to grow forever. 500 bacteria are present initially. I don't know how they counted that. And there are 800 after 1 hour. How many will be present in the culture after 5 hours? And how long is it until there are 20,000 bacteria? This is not decay, this is growth. Good news, it works the same way. If you don't want to use A for the amount of bacteria, you can use P for the population of bacteria, which seems a bit strange for bacteria, but is quite reasonable for other populations. Up to you. Make sure you define your variables. Get started. See how you go. All right, so running through the last one here. We start off with our rule. Eventually. A at time t, so they've just used function notation there. That's fine. Initially, there were 500, so we replaced the 500. After 1 hour, we will have 800. So we substitute in those values for t and for a of t, and we can rearrange this to get the value of k. Natural log of 8 over 5 equals k. Ugly decimal, don't use an ugly decimal. Save it in your calculator or just put in ln 8 over 5 as we had. So now they want to know how many there'll be after 5 hours. I'm just going to substitute in my values for k, t, and a naught. And we get the answer, 5243-ish. Did we agree with that one? Oh, we're finally agreeing on one of the answers. That's nice. How long will it be until there are 20,000 bacteria? So put 20,000 on the left-hand side, and we're going to rearrange and solve for t. About 7.8 hours. That's fairly quick growth, isn't it? Not too bad. I just want to pause for 1 second there and just make note of something, because you may see this written in other ways. We had in our original expression there, oh, that didn't work very well. The total amount, I can write it as a function, that's fine. A of t equals a naught b, and they had the natural log of 8 over 5 times t in my power, didn't they? Are we all happy that that was what our rule was? You will sometimes see this, and this might be useful, particularly later on with some of the grade 12 stuff. I could think about that as e to the natural log of 8 over 5 to the power of t. Because when I have a power raised to a power, I multiply the index, don't I? So that's okay. But e to the log, e to the natural log of 8 over 5 is just 8 over 5. E to the ln of x is just x. So e to the natural log of 8 over 5, I can just use 8 over 5 to the power of t. So have a look, just use that rule and check what we get for the 20,000 bacteria.
It's a bit like if you times by 2 divide by 2. If I have 5 and I times by 2 divide by 2, it's 5.
Yeah.
If I have 5 and I add 2.
That might be a little bit confusing. Let's think about what the natural log of a number is. the natural log of a number is the power I need to raise e2 to equal a number. So the natural log of 8/5 is the power I need to raise e2 to end up with 8/5. So I've got e being raised to the power that it needs to be raised to equal 8/5. So it must just equal 8/5. It all works out beautifully. If we do the same calculation that we did before, I'm going to have 40 equals, that is 40, isn't it? Yeah. Equals 8/5 to the power of t. I can use logs here to solve this, can't I? I don't mind if you use log base e or log of anything else. You could go log of 40 when the base is 8/5 equals t. You can do it on your calculator. Log 40 over log 8/5. Change the base rule, or you could use your log AB button on your calculator. I don't mind which way you do it. Same way. What was the number again? 7.848 hours, wasn't it? That's fairly specific for the number of hours. So we get the same answer we had before. So once you've got a particular growth rate per hour, you can actually use that as the base for your exponential function. So you'll sometimes see answers written in books like that, or other teachers writing answers like that. Handy to know that. Often in physics or chemistry, they just tell you, use this rule. But they don't explain why. I want you to understand why. I think we are done with that.